How are you guys doing today? Good. Let's take a minute and talk about the exam here for a minute before we get started, since I think everybody's here. So the exam format, 15% of your grade, covering chapters 1 through 6. You have 3 questions per chapter. You can skip any 2 questions as long as they're not from the same chapter, so you can't skip like 2 questions from chapter 6 or something. You do 1 from 5 and 1 from 6. But all questions are equally weighted to make them worth 5 points each. Some of the questions might have multiple parts. The parts would then sum to 5 points. So if there's a question where there's part A and B, if you skip that question, you skip parts A and B. So that's 1 skip. Everybody's okay with that? All the exam questions will be a version of an old test question. When I say a version, what do I mean?
Different numbers.
Same problem, different numbers. Exactly right. So every one of the exam questions is going to be an old test question with some of the numbers changed. Okay? You can make a half sheet of notes to use on the exam. You can put anything on it that you would like. You can write on both sides. You have to turn that in by 2:45 p.m. on December 14th. That's the last regular class day before exams start. What would I put on my half sheet if it were me? Oh, I would put on how to do the problems that I got wrong from the old tests. So what am I going to give you? So this is the equation sheet that I'm going to give you.
Does it include the answer?
Okay. Would I waste my time putting any of that stuff on my half sheet?
No.
No way, Jose. What would I put on there? How to do stuff that I got wrong that I still am not confident I can do right without a little bit of help.
Better.
Okay. When I say half sheet, what do I mean? Like half of a standard computer sheet of paper, not like half of a poster board. Nobody get cute on me. Also, has to be handwritten. Okay, you can't like scan a copy of all your tests, like compress them down to like 1/10 scale and like get all the images on there. No. Handwritten. Nobody put like, come in with a magnifying glass and like 1-point font or something. I say it because somebody would try it. Okay? Somebody would do it. Some maniac in here would be like, that's what I'm going to do. Heh. I don't know who the maniac is, but somebody would try it. So I have to say it every year. Yeah, Pierce sounds like that. That'd be right up your alley. Yeah. Look for that loophole, right? All right. Does that feel pretty fair format-wise? Okay. Am I going to make a review for you?
No.
Why would I? What are the test questions or the exam questions? Old test questions. Why would you worry about anything other than old test questions, right? Everybody feel good? Okay. You guys have a good idea what to be reviewing? Yeah. So I would spend, I would gather up my old tests. You notice that we are missing one thing if we're doing chapters 1 through 6, right? What would you be missing?
Chapter 6 test.
Chapter 6 test. Look at what else is in here. Here's a version of chapter 6 test that I would have given if there were enough time. So you have something to look at, to work through. And how would I know what's right or wrong? Well, I put the key in there with the worked out solutions. Okay. Feel fair? Pretty clear as to what to do to prepare? Feel like you can have a chance at doing well? Like it's narrowed down enough that you get enough little extra help for yourself with the half sheet? Okay. All right, dudes. That feels good to me. You guys feel good? Okay. Today, then, let's pick up where we left off in chapter 6, eh? So last thing we talked about in chapter 6 was these power-reducing identities. Today, we're going to talk about the half-angle identities. And to get that, or to derive the half-angle identity, I'm just going to start with the power-reducing. So if I get that, let's say I want to start by doing the half-angle identity for sine. So I'm just going to start with my power-reducing. And then I'm going to make a substitution. I'm going to substitute in for u theta over 2. So 2 times theta over 2 is just theta. Everybody feel okay with that? And now I just got to get rid of that squared on the sine. So square root both sides. Unfortunately, what is that going to give me? Plus or minus. Excellent. Oh, sure. You'll need that. Okay. So that's the half-angle identity for sine. I'll drop in the formulas for all of these. Oops. Need some more space there. I would derive the rest of these similarly. What do you notice here when you look at the rest of these half-angle identity formulas? Three options for tangent, right? Does it matter which one you choose? No, man. They'll all work. But does it matter which one you choose if you don't want to make your life difficult? Yeah, so you probably need to spend a minute and kind of think about which one is going to make your life easiest when doing that kind of thing. Okay. So, oops, that's not what I wanted to do. So let's do a couple of examples here. So it says here to use the half-angle identities to find the exact value. So we have cosine of 75. 75 is half of what angle? (150), correct? Oops. Mr. Kulik, come on now. There we go. That's more like it. All right. So what do I do? I go up to my identity. So I'll just fill that in. So I have plus or minus 1 plus cosine of 150 over 2. All right, before we keep going, I'm going to pause here and figure out whether I want the plus or minus. 75 degrees is in quadrant 1. In quadrant 1, cosine should be positive. So I'll drop the minus and we're just going to use the plus. So easy to do that. You just have to remember, it's easy to forget. All right. So cosine of 150 is, it's in quadrant 2, so I know it's negative. Square root 3 over 2. Everybody's so far so good? Now I'm going to multiply the top and bottom by something to clear out that little fraction inside of my big fraction. Here's the million-dollar question. What am I going to multiply to the top and bottom? 2, right? Everybody says 2? That's wrong. Where that 2 needs to go underneath the radical, correct? So it should be the square root of 2 over the square root of 2. If I want to multiply two radicals together, or if I want to multiply something inside of a radical, it's got to be under a radical also, right? We see that. That's why it was the million-dollar question, because every time I ask it, we all screw it up initially. And then when I tell you what it is, you're like, oh yeah, yep, need a square root around that. And then my last thing, I noticed that the 4 in the denominator, that's a perfect square, correct? So I'll do that. Everybody's cool? Not a big deal, right? These ones always give students headaches. What's half of 9/8? Or 9/8 is half of what, I should say? That's the question I want to ask. 9/8 is half of what? 9/4. There you go. Fractions are hard, guys. The way I always have to remind myself is like, what's half of a half? A quarter, right? So like a half divided by 2 is a fourth. It's getting the denominator just is multiplied by 2. So you just divide the denominator by 2 and that's all you need. So I'll use my half angle identity from above. Okay, let's make a decision about whether we want the plus or minus. 9 pi over 8 is in what quadrant? Oh, guys, what quadrant is 9 pi over 8? It's quadrant 3, right? It's a little bit past pi. So we're in quadrant 3. In quadrant 3, sign should be?
Negative.
Negative, right? Because the y coordinate is negative. in quadrant 3. Great. And then, okay, so if I go to my unit circle and I do cosine of 9/4, oh no! Is 9/4 on my unit circle, or 9 pi over 4 in my unit circle? No. What do I do? I would not add, but subtract 2 pi to find an angle that's coterminal to that. Specifically pi over 4. Now I go to my unit circle. Pi over 4 is root 2 over 2. What am I going to multiply by to get rid of that little fraction? Redemption time.
Like 2 over 1.
Square root 2 over 2. Right? We got to have that square root around everything to go in. Oops. Don't forget your negative, Mr. Kulik. I was going to remember. And then the denominator, I notice, is a perfect square, so might as well reduce that. What do you guys think? It's okay so far? Okay. Let's do the last one there. Uh-oh, what do you notice? Yes.
Sorry, in a previous question, why did you multiply by root 2 again?
So I need whatever I'm multiplying here to go like inside of the radical to be able to multiply like a times b. Well, that's just b square root a, right? But if I have square root a times square root b, that's square root ab. That's what I want to have happen.
Okay.
So I need the square root around that in order to multiply it inside of the radical.
Okay.
Does that make sense?
Yes.
Okay. So again, just like you probably get the right answer even if you're doing it wrong, but like let's try to make sure we're doing it right. You know what I mean?
Yes.
Yeah. Because it will matter eventually. Okay. So cotangent of negative 105. One thing you should notice right away. Well, even before that. What do I have identities for? Sine, cosine, and tangent. What is this one? Cotangent. Oh no! What in ever will I do? Well, I'm just going to be thinking about it as like the reciprocal of tangent, right? Notice the negative 1 outside like that is a reciprocal, not the inverse tangent function. Don't get confused on that. It's easy to make that mistake. The notation can be confusing. Okay. So I'm going to rewrite 105 as a half of what angle? Well, that'd just be 210. Oops, I used a square bracket there. Okay. Here's the big question. We have 3 choices. Which one would be the best choice? Which one can I throw out immediately? Which one do I want no part of? Yeah, that top one, I want no part of that. Like, I don't want a radical if I don't have to. I don't want the plus or minus to deal with if I don't have to. Like, give me something else. All right, between 2 or 3, which one do I want?
3.
3 would be the better one, yeah. Why?
Because if you do number 2, you have to do like 1 minus, the cosine of minus 2.
Here's the, well, maybe, but here's what I'm concerned about. Is I'm going to flip this at some point, right? I don't want to have like 1 plus a radical in my denominator where I have to rationalize that by multiplying by the conjugate. That's like kind of a lot of work. But if I take 3 and I flip it, this piece that would be now in the numerator, and I just have a single thing in the denominator. So if I have a radical in the denominator, just like multiplying the top and bottom by like square root 2 or something, it'll be easy. So that's my motivation, is I want to avoid having to like rationalize the denominator by multiplying by a conjugate. That's the thing that I want to avoid. But 3 is the one that I would choose. Oops. So let's go ahead and do the reciprocal. And at the same time, I'm going to find an angle coterminal to the negative ones, right? If I add 360 to 210, I get 150. So I'm going to do both of those 2 steps at one time. Is everybody okay with that? So doing the reciprocal gets rid of that negative exponent. And then I'm going to add 360 to both of those angles so I have something on the unit circle. You could have also used like your odd-even identities and just turn that into negative sine 210 and cosine of 210. That would be okay to also if you wanted to go that route. Not really any more work. Cosine of 150, we did that already, didn't we? And sine 150. We did already, right? We did that on which one? There, this cosine 150. I guess we didn't do sine 150, but. And then I'll just multiply the top and bottom by 2 over 2. Since there's no radical there, I don't need a square root on it. Notice that if I had chosen equation 2, at this step, it would have been flipped, and I'd have to multiply by a conjugate, and then it's like a whole thing, right? I don't want to mess with that. I'll take this one. Oh my goodness, guys. Cosine of 150 is negative square root 3 over 2. Great googly moogly. It's like, that didn't look right. That should have been a negative number, or not that big of a number. Right? Mr. Kulik knew something was up because 2 plus the square root of 3 is bigger than 1. And, oh, I guess it's a cotangent. I guess it's not unreasonable. It's bigger. Anyways, I saw something was up. All right. Doing okay still? What's the other kind of problem that we do with these identities? So we prove stuff. Do an example of that. So we have proved the identity 2 cosine squared x over 2 times secant equals secant x plus 1. Well, my suggestion to you would be work on the side where you see the half angle identity. The left-hand side, since it's asking, we just learned about half angle identities. Now, technically speaking here, I could use a power reducing identity here, or I could use a half angle identity here. Either will work. Since we're in the half angle section, I'm going to use the half angle identity here, but you could have used power reducing. That would be okay too. So cosine of x over 2 is square root 1 plus cosine x over 2. And because it's cosine squared, I'm going to have 2 of those. And then I'm not going to multiply by, we're not going to change secant squared, because in my answer I'm supposed to have secant squared. Right? Did I write that down right? Okay, good. Oops. Forgot the plus or minus. Okay. Everybody feeling okay? Now I love that squared was on my cosine x over 2, because what's that squared going to help me get rid of? The radical and the plus or minus, right? Because if you square something, it's got to be positive afterwards. So that's really nice. Everybody cool there? Cancel the times 2 and the divides by 2. And then I'm going to rewrite cosine as 1 over secant. And I usually don't rewrite like cosines as like 1 over secants or whatever. But my answer has secants in it. So like rather than turning secant into 1 over cosine, distributing things through and then turning them back into secants, I'm just going to use one identity and turn the cosine into a secant. Distribute my stuff through. And I have secant x plus 1, which is what I'm looking for. Yay! What you guys think? Feels just like chapter 5, doesn't it? There's more identities to choose from, but it's still just like chapter 5. Okay. 6-4. We're going to finish up here today. We're going to be a day ahead of schedule, but that's okay. I'm sure nobody will mind that you have more time in class to work on exam stuff. Okay. So we've been doing proof. Okay. Yeah, Pierce. Sure. We've been doing proof throughout, right? What's going to be different now? Nothing, except you're not given like, use the blah, blah, blah identity to prove this. Now you have your choices. So again, if I look at this, I'm going to start with the left-hand side because I see that I can easily apply my new identities. So when I see 2 alpha, I can either think about that as a double angle identity, right? Or I could think about it as alpha plus alpha and do it as a angle sum. Or I could even be tricky and make it like 3 alpha minus alpha and do it as a difference or something, right? Now, given my options, which one do you suppose I'm going to choose? I'm going to do the double angle. Typically, that's going to be the easier route to go. when you have a 2 coefficient. But I notice that my double angle identities don't have a cotangent version, right? Oh, those are power reducing. I didn't have the double angles in here. Do we need to look at them? I'll go find them real quick. There they are. Okay. So I'll use then my double angle identity for for tangent, but I'm going to flip it while I do it. Is that okay with everybody? I'll reduce the 2's. And now I'm going to rewrite this as 2 fractions with a common denominator. I'm going to rewrite as 1 over tan alpha minus tan squared alpha over tan alpha. Everybody's cool with me why I can do that? I'll reduce that second fraction. 1 over tangent is cotangent. So there's my cotangent alpha. And then what's left after I did that reducing was tan alpha. And that's exactly what I needed. And I'm done. What you guys think about that one? Not a big deal. Let's do another. Okay. Uh-oh. Cosine of 4x. Oh. What am I going to do with that? I don't have a cosine 4x. Well, I am going to start on that side. I'm going to think about cosine 4x as, here's the trick, 2 times 2x. Now it looks like a double angle, right? All right. Here's the $100 question. I have 3 possibilities for the double angle for cosine. Which one of the 3 should I pick? Look at what I'm trying to get to. I'd use 3. Because 3 gives me the 1 minus. I'm supposed to have a 1 minus in my answer. That looks good to me. Everybody agree or see the reasoning there? Could I have used another one? Sure. Could it have gotten potentially quite messy? Yeah, maybe. So I have 1 minus 2 sine squared 2x. Why is there a sine squared 2x? Because 2x was like my u. Everybody can kind of see that. Got to be a little bit careful with that. It's easy to kind of goof that up. Okay? And then sine squared 2x. What do I want to use on that? I could use a power reducing identity. I would pass on that option. What I would use is that. The double angle for sine, because look what I'm supposed to have. Sine squared times cosine squared, right? Do you see that in the double angle for sine? Yup. That seems like a good deal to me. So sine squared 2x gives me the identity for sine 2x squared. Everybody's good with that? And this 2 here is still that 2 there. Okay. When I square a product, how do I do that? If I have like 2 square root of 2 squared. Right? We have to square both parts of the product. So 2 squared, sine squared, cosine squared. And then, whoa, 2 times 4 is 8. And wow, look at that. I got my answer. I am so smart. SMRT. You guys feeling okay on these? I kind of think these ones are easier than the other ones, even though like it looks kind of chaotic, but the identity is really just kind of like everything slots into place pretty nicely. There's less weird algebra tricks on these ones than there were in the chapter 5 ones, in my opinion. Let's do some solving examples, right? That was the other thing we did in chapter 5. So remember, a problem like this in chapter 5 was kind of a nightmare because of the 2x. Right? Guess what's going to be a heck of a lot easier now? Problems like this with the 2x. You know why? Because my first order of business is to use an identity on that to get rid of the 2. I'd use a double angle. Now, this is an actually very important question because here is it makes life considerably easier if you choose wisely. Which one of those versions of cosine should I choose? 1, 2, or 3? You should pick 3. Why? Because so I only have one kind of trig function in my problem. All I'll have is sines. Everybody's good with that? Okay. What does this equation kind of remind you of? Think back to last year in your math class. Looks like a quadratic equation. Yeah, something that you could potentially factor. So to solve a quadratic, what's the first thing you need to do? It has to equal 0. So I'm going to add the sine squared to both sides and then subtract 1. Everybody's cool there? So now I can solve this by factoring, or I could use the quadratic formula. Does it matter which one I use? No, it doesn't. They both work perfectly fine in this case. Could it matter which one I use? Yes. Is every quadratic factorable? Over the rationals anyways? No. Some of them are not factorable over the rationals, and you'd have to use the quadratic formula. This is not one of those cases. Let's just review how we would use the factoring here. So I need two numbers to multiply to give me something and add to give me something. What do they need to multiply to give me? -2. Remember, the leading coefficient isn't 1. So this is A times C. Has to be add to, or multiply to give me -2. What does it have to add to give me? +1. What are those two numbers? Guys, it took too long. How that wasn't instantaneous, I don't know. Okay, what do I do with those two numbers now? They tell me how to split up the linear term in my quadratic. I'll make two groups. From the first group, what's my greatest common factor? 2 sine x. When I factor that out, I'm left with a sine x plus 1. What's the greatest common factor in my second group? -1. That leaves me with a sine x plus 1. Notice that these are in common between each term. So when I factor the sine x plus 1 out, I have 2 sine x minus 1. I can now apply the zero product property. So where is sine x equal to -1? 3 pi over 2? Where is sine x equal to 1/2? Pi over 6 and 5 pi over 6. And I think we asked for just on the interval from 0 to 2 pi, so those are our answers. Notice that I have to do the, find the infinite cases and then, go through, checking all the values for k to make sure things were landing inside my interval? Nah, man. Why not? Because when I solved, I always just had an x. We used the identity to get around having to do that. Right? That's really cool. It was really cool, guys. Really cool. Let's do another. What do you guys say? Hey, what do you say? What do I got? I got this example and one more example, and then I think I'm done for the semester. Woo! Did Mr. Gulick just use the D word? Yup. All right. So solve algebraically on the interval. First order of business. I gotta do something about that 2x there, right? What do you suppose I'm gonna do? Double angle identity for sine. Okay. Everybody's happy with that? Just use the double angle identity for sine. That's where the 2 sine x cos x comes from. To solve this now, what do I do? Divide both sides by cosine, right? No! Remember last time we talked about this? What do I want to do to solve this? Got to get it equal to 0 and we got to factor. Yes. Should have been faster. I wouldn't have had to yell. That's okay. I'm just teasing you. I liked yelling. Okay, how do I factor this? Greatest common factor of 2 cosine. I think I heard people whispering. So we can apply the zero product property now. So the first one, I'll divide both sides by 2. And cosine is equal to 0 at pi over 2 and 3 pi over 2. But look at the interval that I'm solving on. So what do I need to do? Yeah, I'm going to subtract 2 pi, right? So that gives me negative 3 pi over 2 and negative pi over 2. Or either those in between negative 4 pi and negative 2 pi. Nope. So what do? Just subtract again. That's going to be negative 7 pi over 2 and then negative 5 pi over 2. Those two work. Everybody's okay there? All right, let's deal with this other equation. This looks kind of scary because I got a sine and a cosine together. Who remembers the trick? I'm going to make a tangent. So I'm going to subtract a sine over. Then we'll divide both sides by cosine. Mr. Kulik, you told me we weren't supposed to do this. I know, but it's okay because I'm not getting rid of anything, right? The cosine just stays in the denominator. That's fine. And sine over cosine is tangent, and I'm just going to divide both sides by negative 1 at the same time. Everybody's cool with that? Where's tangent equal to negative 1 at? Second and fourth quadrants at 3 pi over 4 and 7 pi over 4. Are either of those inside the interval I'm looking for? No. How many times am I going to have to subtract 2 pi to get something that is? Twice, right? I'm going to do it just all at once and subtract 4 pi. Everybody okay with that? So that's going to be what? Negative, that is 8 pi, or 16 pi over 4, so that's going to be negative 9 pi over 4. And that's going to be negative 13 pi over 4. Now, we're not done. I shouldn't have circled these yet. Why not? Why not? I'm going to uncircle these because I'm not quite done. Oh, wait a minute. No, this is going to be okay. It's okay. All right, let's pause and explain what Mr. Kulik was worried about. Mr. Kulik was worried because tangent can be undefined, right? And it's specifically undefined where cosine is 0, because it's sine over cosine. What are these solutions coming from? Where cosine is equal to 0. Uh-oh. So these ones shouldn't count, right? No, it's fine. Because if I go back to my original equation, there's no tangents in that. I made the tangent later on. So the extraneous solutions for the tangent don't matter. If there were tangents in my original equation, then for sure I would have to go back and check for extraneous solutions. However, since I was the one that made the tangent, if I go back and check, these values don't create something undefined in my original equation. So they're okay. So this didn't matter. Those are my two solutions. You guys kind of see what I'm saying? This was like when you solved rational equations last year, you had to go back and check to make sure your solution didn't give you a 0 denominator. Same idea here. Now, even though this gave me a 0 denominator, it didn't give me one in the equation, the original equation, the one that mattered. My apologies for hemming and hawing about that. What am I doing here, you doofus? Take the whole thing. Okay. First order of business. I want to get rid of the coefficient on my variable, right? Okay. What am I going to use to do that? I'm going to use the half angle. Now, because it's sine squared of theta over 2, I know whatever that comes, or whatever I'm going to create from the half angle is going to be squared, right? Oh, okay. You hear that buzzing? That's the fan on my projector. Isn't that awesome? Let's hurry up and finish so I can turn it off. Who's ready to smash something? This is me all day. This is why I'm insane. Okay? School is slowly driving me crazy. It's not that slow. All right. First order business. Let's do some simplifying. I'll also notice that the 2's are going to reduce also. I'm going to do that all at once. Everybody okay? Oh boy, these are two different trig functions. I can't do that tangent trick here. What should I do? What can I do? Can I rewrite sine squared in terms of cosines? Heck yeah, I can. Sine squared is 1 minus cosine squared. Oh, yeah. And then I can subtract 1 from both sides. Get those guys out of there. Let's add a cosine theta to both sides so that it's equal to 0. I'm not going to divide both sides by cosine. Rather, I'm going to move everything onto one side and factor. Once I'm factored, we'll use the zero product property. Cosine is equal to 0 at pi over 2 and 3 pi over 2. I'll subtract 1 from both sides and then divide both sides by 1. Cosine is equal to 1 when x is 0, but not at pi, right? At pi, it's -1. And I think this was all solutions. So I can take my answers here and stick a 2 pi k on to the end of them. Or, if you're into that whole brevity thing, these two you could condense together into 1 by just writing as pi over 2 plus 1 pi k. Either is fine. Right? So you could write it this way, or write it that way. Sure thing. Guess what, my dudes? We're done. We're done with stuff for the whole semester. Yes. Yes. All right. So, what are we going to be doing in class the rest of the time? You're going to be working on your review stuff. So, reworking your old test questions, putting together your half sheet. If you want to be working on this final problem set, if you're somebody that's like, well, I got a lot of missings, I better do it. But remember, one homework assignment is dropped if you have everything turned in. There's one homework assignment that's dropped. If you have everything turned in, you do not need to complete the last homework assignment. Now, I know you'll do some practice because you're excellent students and you know Chapter 6 is going to be on the final, but you don't have to worry about doing all of them and getting them into OneNote or whatever, because there is a homework assignment being dropped. Correct.
What do we have to do?